Okay, so in the last slide we were talking about multiple bonds, and we were looking at a bond between two atoms. So here we have a multiple bond between a carbon and another carbon. So this was the ethylene molecule that we showed in the Lewis dot structure, where you have a pair of electrons between each pair of atoms here. Between this carbon and this carbon, we actually have a multiple bond. This is my sigma bond, because the bond is between the two atoms. Now what's this? This is what you have in your multiple bond. So the electron density in the multiple bond does not lie between the two atoms. Why not? Because it already has a bond between the two atoms. So you can't put extra electrons where they already have a bunch of electrons. So your pi bond, your second bond, your multiple bond, so the first bond would go in like that. Your multiple bond is going to go in like this. So this is half of the pi bond. This is the other half of the pi bond. Please also note that you have wedges and dashes. So these wedges represent things that are coming out towards the viewer from the plane of the board. This represents things that are going back away from the board and away from the viewer. So wedges coming out at you, dashes going away from you. So we have a double bond here. We have two pairs of shared electrons. So one of them is a sigma bond and the other is a pi bond. So when you have a pi bond, it's like a donut. So here's the pi bond, and there's actually absolutely no electron density for this pi bond between the two atoms. It's actually above and below. So when you have a triple bond, you're going to have one sigma bond, so one sigma bond, and you're going to have two pi bonds. So whenever you have two atoms combined together, they always have one sigma bond, and then the other, any additional bonding has to be some sort of a pi bond, because you already took up the space between the two atoms. So let's talk about molecular shape. So here is the shape of methane. It's actually tetrahedral. It looks like that. Here's my molecule of ethylene. So this is actually absolutely flat, but the angle here is around 120 degrees. Angle here is around 120 degrees. Here's my acetylene molecule. So this is all in one line. So the bond angle here is 180 degrees. So how do you get bond angles? You can't really get bond angles just by using S and P orbitals, because if you just do S and P orbitals, everything would be 90 degrees. So you actually have to look at valence shell electron pair repulsion theory, or called VSEPR by some people, or VSEPRT by others. And you use this to explain the molecular shape of molecules. So in VSEPRT, you have hybridized orbitals. The reason why you have hybridized orbitals is because when you hybridize orbitals, it is lower in energy, because when you hybridize orbitals, the electrons can get far away from each other than they would be able to do if you did not hybridize orbitals. So how do we do VSEPRT? First, you have to draw the correct Lewis dot structure. Then you count the number of electron domains around the central atom. So when you count single, double, and triple bond, you count that as one electron domain, or a sigma bond is one electron domain. And then one lone pair you count as one electron domain. So in this case, this carbon has 3 electron domains. This carbon has 4 electron domains. This carbon has 2 electron domains. So even though there are 3 pairs of electrons here, I'm only counting it as 1 electron domain, because we're really only counting the sigma bond. After you come up with the electron domain, you use the following chart on the next slide to assign electron shape. So you probably already did this in general chemistry. You might have forgotten, but I'm going to give you a chart, and I'm going to just memorize that chart, because it's not really that much there. The other thing you want to remember is that in general, electrons try to stay as far away from each other as possible, and also electrons are invisible. So if you have a lone pair, you don't count that as being that geometry showing that electron as being there. So here is the molecular shape VSEPRT chart. So we have electron domains, the shape of the electron domains, we have the number of lone electron pairs, we have the shape of the molecule, we have hybridization, and we have bond angle. If you have two electron domains, the shape of the electrons is linear because the electrons are trying to get away as far away from each other as possible. If you have zero lone pairs, the shape of the molecule is linear. The hybridization is sp and the bond angle is 180. If you have three electron domains, the shape of the electrons is trigonal planar. If you have zero lone pair electrons, the shape of the molecule is trigonal planar because all three of the electron domains have an actual atom there. So it's still, the shape of the electron is the same as the shape of the molecule. The hybridization is sp2 and the bond angle is 120. If you have three electron domains, so you have the shape of the electron trigonal planar, but you have one electron lone pair, you can't see the lone pair. So instead of looking trigonal planar, you can't see one of the triangular things. So it looks bent because you can't see electrons. It still has the same sp2 hybridization. It still has the same 120-degree angle between the atoms that are there, or between the atom and the electron. The bond angle is still the same. It might be a little bit. Electrons tend to occupy a little bit more space than an actual atom. Bond to an actual atom, so the position of the electron is going to have occupy slightly more space, so the bond angle is going to be a little bit distorted, but essentially it's going to be 120 degrees. If you have three electron domains, the shape of the electron is trigonal planar, but you have two lone pairs. That means that two legs of your triangle are invisible, so it's just going to look linear. Same hybridization, sp2, bond angle, still 120. Well, obviously, if you only have two atoms, then you can't really see the 120-degree angle. It would look linear, so it just would be 180 degrees. If you have four electron domains, the shape of the electrons is tetrahedral. If you have no lone pairs, the shape of the molecule is also tetrahedral, because on each of the ends of the electron domains, you have an atom. So it looks like the same shape as the shape of the electron. The hybridization is sp3, the bond angle is 109.5. If you have the shape of the electron tetrahedral, so this would be if it still has four electron domains. If you have one lone pair electron, that means that it is trigonal pyramidal. Why is that? Because if you remove one of the legs of a tetrahedral, then it looks trigonal pyramidal. I'll have to show you this structure in class because you probably can't visualize it. Although I suspect that you really should have covered this in general chemistry, so this should be reviewed. So I'm guessing that you probably had to memorize this for general chemistry. You probably had to memorize not just the tetrahedral, you probably had to memorize octahedral and trigonal bipyramidal. Hybridization is sp3, bond angle is still 109.5. Okay, so if you have two lone pairs, then two of the legs of the tetrahedral are invisible, meaning that the only thing that you can see is something that looks bent. Once again, same hybridization, sp3, bond angle still 109.5. Between the atoms that you can see, it's going to be it'll be slightly less because the electrons generally, lone pair electrons tend to take up a little bit more space than bonding electrons. If you have three lone pairs, I mean really you just have a single thing, so then it's linear because you can only see two atoms, and then the other parts of the tetrahedral are all invisible, so it just looks linear. Still has the sp3s. I mean it's linear, so it really doesn't have a 109.5 degree angle. Okay, so you want to memorize the chart that I showed you earlier. So what about these hybrid orbitals? Here's my sp hybridization. So when you do hybrid orbitals, it's like mixing one s orbital with one p orbital. So the combined is going to have the characteristics of both an s and a p. So if you mix white and pink, the stuff that you end up, white and red, the stuff that you end up is going to look pink. So it's sort of the same thing. I think I heard that you mix a donkey with a horse and you get a mule that has the characteristics of both or something like that. So anyway, this is what you're doing for hybrid orbitals. So here we're taking, for our sp, we're taking one s and we're adding it to one p. So here is my s, here's my s and here is my p. So my p has a positive lobe over here, you got a negative lobe over here. You get destructive interference, so you have a small lobe over here and you got a big lobe over here like this. Here's my sp hybridized orbital. If you combine it with a p orbital that's pointed in the other direction with a charge going in the opposite direction, then you end up with this. The bond angle between the two parts of the sp hybridized orbitals, it is actually 180 degrees. What happens if you have an sp2 hybridized orbital? Well, you take one s, you take one p, you take another p. Now, the p orbitals always come out x, y, z, so this is like a Cartesian coordinate x. So this p orbital is along the x-axis, this p orbital is along the y-axis. So when you combine them all together, you end up like this. You end up with our three sp2 hybridized orbitals. So if you mix one s and two p, then you end up with three orbitals. Whatever orbitals you put in, that's the same number of orbitals you get out. So if you mix one s and two p, you mixed in three orbitals, you're going to get out three orbitals. So you start out with three, you end up with three. So here is my sp2 hybridized orbital. When you combine them all together attached to the same carbon, you end up looking like this. And you notice that the bond angle between that sp2 hybridized orbital and that sp2 hybridized orbital is 120 degrees. So then you get something like that. Now, when you have an sp2 hybridized carbon, one of the p orbitals is not hybridized. It's just sitting there as the pz. So here's my unhybridized pz orbital. Here are my hybridized p orbitals mixed in with the s. So here is my unhybridized p orbital. You use this to form pi bonds. So three orbitals combine to form three sp2 hybridized orbitals. You get trigonal planar geometry, 120 bond angle. So what about sp3 hybridized orbitals? You take one s, you take three p's, p in the x direction, p in the y direction, and p in the z direction. You combine them together, you end up with this. The bond angle between the four sp3 hybridized orbitals is 109.5. So you got four orbitals going in, one s and three p. You get out four sp3 hybridized orbitals. And the atom has a tetrahedral electron pair geometry, and the bond angle is 109.5. So here's the structure of methane. So here's the Lewis dot structure of methane. You can also draw it with this wedge dash drawing where this is coming out at you, that's going back behind the plane. This bond angle is 109.5. This other bond angle is 109.5. The bond angle between these two hydrogens is 109.5. The bond angle here is 109.5. You can also see what a three-dimensional structure would look like if you actually had like a little ball and line kind of little model set. So it looks like this. You can also draw it like this, where you sort of have surfaces between that hydrogen, and that hydrogen that forms one plane, and so on like that. You can also show it with the hybridization. So here's my sp3 hybridized orbital, sp3, sp3, sp3. Here's my s orbital for the hydrogen, and here's the bond. And this is a space filling model for the same thing. So here's a solved problem. So the solved problem is you're to predict the VSEPRT shape and hybridization of the nitrogen atom in the molecule ammonia. You are to draw the picture of the three-dimensional structure of ammonia, and you're supposed to predict the bond angle. Okay, so here's my solution. So we're going to do VSEPRT electron domains. So we have 4. If you draw the Lewis dot structure of ammonia, you'll see that you actually have 4 electron domains. You have 1 lone pair. You have 3 electron pairs, so that gives you a grand total of 4. So the molecular shape, so here's my Lewis dot structure. So it's got 1 lone pair and it has 3 sigma bonds. So it has 4 electron domains. So if it has 4 electron domains, then the geometry of the electron shape, or the electron shape or the geometry of the electrons, is tetrahedral. Now one of these is a lone pair. You can't see electrons. You can see atoms. That means that one of the legs of the tetrahedral molecule is invisible. It still has the same hybridization as it would have if this actually was an atom. So that means that it has 3 electron domains. The 3rd domain is non-bonding or lone pair. The hybridization is sp3, and you have tetrahedral geometry, so all of these bonds are around 109.5 because you would have memorized that little chart that I gave you to memorize. So here is the 3-dimensional structure for that molecule. Now, if there was something attached here, if there was an actual hydrogen over here or something like that, then the structure of the molecule would not be trigonal pyramidal. It would actually be tetrahedral. But electrons are invisible, so you can't see this. All you can see is the nitrogen and these 3 hydrogens. So what does it look like? It looks like an Egyptian pyramid with a triangular base. So that's why it's called trigonal pyramidal structure. Lone pairs occupy a little bit more space than a regular bonding electron. So this is slightly less than 109.5.